Hey guys, welcome back to e-learning lesson number 4. It's going to be a fairly simple one today. If you were looking for a topic that was going to be hopefully fairly easy and straightforward, this is the one for you. This will probably be the easiest thing that we do for the rest of the semester. So listen up so that way you get a good grade on it, because the thing that will come after this assignment, so e-learning lesson number 5, the next one, will be a little mini quiz on this. So hopefully that'll boost people's grades up a little bit. So what this is about is a very practical topic, which is how do you speed up a chemical reaction? How do you make something go faster? Or in reverse, how do you make something go slower? So if you want to speed up a chemical reaction, there are 4 things you can do. You can add heat, so like you can increase the temperature. You can increase the concentration of the substance that you're putting in. So for instance, if I was, we've done experiments where we mixed magnesium metal. You guys remember it was like a little silver strip of metal with some hydrochloric acid. And if I increase the concentration of the hydrochloric acid, the reaction is going to happen much more quickly. That reaction, if I'm trying to jog your memory here, was kind of a fizzing. It was releasing the hydrogen gas, and you guys remember I had you stick that wood splint into the test tube, and it made a little poof sound, and a little flame came out because hydrogen gas is flammable. That's an example of a chemical reaction that could be sped up if either I added more magnesium, so more metal strips into the test tube, or I added more concentration of hydrochloric acid if I increased its molarity. You can increase the surface area of something by crushing it up. So if you're able to expose more parts of your chemical to the surrounding environment, you're going to get a quicker reaction. And you can add a catalyst. And a catalyst is something that is used to make a chemical reaction go quicker, but it's not used up through the reaction. So it's kind of like an enzyme, if you remember back to biology. So I got a simulation that'll help you to visualize 2 of these things. So let me bring that to you right now. We got, this one here. Now the first one we're going to do is temperature. And I know this is a lot to look at, so let me just try to break it down for you. There are 2 screens here. In this area, the temperature is 20 degrees Celsius. So that's about room temperature. Like if you pour water out of your sink, it'll be at around that temperature. Over here in this box, everything in this box is at 80 degrees Celsius. That's pretty hot. That's a little bit under boiling. And you have 2 different types of particles. You got A particles, which are green. You got blue particles, you got B particles, which are blue in color. And right now they're separated, but when I click play down here, they're going to mix. And when they interact with each other, like when they physically touch each other, they're going to make C. Because, we do a lot of chemical equations where we talk about what gets added together to make another product, but in reality, they need to touch. They need to actually interact with each other. So let's see what happens when I push play. Remember, this side's really cold, this side's really warm. The product that we're making is C. As you can see, a lot more quickly being used up, the A and the B particles, to make C particles over here. Over here, much more slowly. And if we think back to the example that I did for you in class, the demo with the hot and the cold water where we dropped in dye at the same time, you should remember that as well. Remember how the dye swirled around and it mixed up a lot more under hot temperatures? That's what you're seeing here. You're seeing this quicker movement on the hot side than on the cold side. And when things are moving quicker, they're bound to collide into each other more often, and you're going to get your product much more quickly. That's why oftentimes they talk about doing things under warm conditions if you're trying to get them to go to completion, like this one. All the pieces found each other, the reaction got completed. All right, so that's temperature. Hopefully that one is probably the most straightforward. You increase the heat, the particles move faster, they collide more, they make your product more quickly. All right. The other thing you can do is you can increase the concentration. Now, this is a little bit difficult to understand, so let me explain. These brackets mean concentrations. This is saying that the concentration of A is equal to the concentration of B. And unlike last time, the temperature is the same on both sides. So it's both 20 degrees, both just normal room temperature water. But this is saying, hey, my concentration of A is equal to 2 times my concentration of B. And that's what you're seeing here. The green particles, I wish we wouldn't do that all the time. The green particles, there's a lot more of them on this side than there are over here. So I increased my concentration of A. And what you should see, it's not going to be as easy to notice, but you should still notice it. You're going to have a quicker reaction on this side than on this side because there's more A particles over here. So more stuff means you're more likely to bump into, an A is more likely to bump into a B. So let's watch. Let me try again. Let's watch. So you see that it is going a little bit quicker on this side. Not by much, but it is going quicker. And you're winding up with a lot of A left over because you had twice as much A as you did B. So there's a lot of green particles left here. All right, so the other one that I wanted to talk to you about, the other two I should say, is increasing the surface area. Now, if you've ever had a jawbreaker, you'll know that it takes a long time to get to the center of that candy. That's because this has a really low surface area. If you put a jawbreaker in your mouth, what you're going to wind up seeing is that your saliva is only interacting with the outside layer. So all these inner layers are protected from what's dissolving the jawbreaker, which is your saliva. So it takes a long time to get through them because it has a very low surface area. However, if I was to take this same jawbreaker, take a hammer, pound it, and make it into a bunch of little dust, and then put that in my mouth, it's going to dissolve much more quickly because I'm increasing the surface area. I'm increasing how much area there is on the surface by making it a bunch of tiny particles. The mass hasn't changed. It's still the same amount of mass, but how I'm interacting with it is changing because I'm making it into a much finer powder. So if you increase the surface area, you're going to increase the speed of your reaction. The last thing I want to talk about is a catalyst. And catalysts are usually enzymes, although they don't always have to be. So if you don't remember from biology, the way an enzyme works is you have your two substrates. So that would be like our two reactants. And normally they would find each other, but it might take a while. They could find each other in nature, but it might take a while. And then once they found each other, they make a product. But what the enzyme does is it provides a spot where they can bind and stick to so that they can find each other much more quickly because they're really close to each other and they can form their product. Like I said at the start, one thing I want you to notice is that the enzyme is not used up in the reaction. So the enzyme, aka the catalyst, doesn't change from start to finish, but your reactants and your products do. You start like this, you end like this. So all a catalyst does is just speeds up the rate of a chemical reaction. All right. And the reverse is true too. So if I wanted to slow down a chemical reaction, what would I do? I would take away heat. So I'd make it colder. I'd add some ice. I decrease the concentration so I wouldn't use as much reactant. I would decrease the surface area. I tightly pack things together, and if I had a catalyst, I would take it out. That would decrease the speed of a chemical reaction. All right. So for your homework today, I have your own little simulation over here, and I would suggest starting with control. If you go and have this, you're going to have A particles in blue, B particles in red, and your finished product is going to be C. If I push start over and I push run reaction, I got the A in blue, the B in red. There's no finished product C because we haven't started yet. When I push run, they're going to interact with each other, and they're going to slowly become C particles. Now, if I want to see how that's going to be affected by temperature, let's click on temperature. Let's click increase run reaction. And we could see that it's a much quicker reaction when the temperature is increased. And you could even see that visually over here. So your homework is going to be revolving around that. It's going to be working on this sort of stuff right here. Okay? If you have any questions, please feel free to email me. And have a good rest of your day. Goodbye.